name's Charlie Caputo. This is a semi-autonomous control interfaces for surgical robots, mentored by Dr. Ahmed Saidi. For this project, we're going to go through the context, the project overview, the proposed solution, and the current prototype, then next steps, and then a quick Q&A. So robotic-assisted surgery, it's been around for a couple of decades now, and has revolutionized modern medicine by adding things like tremor filtering, motion smoothing, which increase reliability and efficiency. With robotic-assisted surgery, or RAS, we introduce a topic called levels of autonomy, also known as LOA. At LOA 0, we have a robot in the loop, but it's fully teleoperated with zero filtering, zero assistance, just pure teleoperation by the surgeon. At level 1, we start to introduce things like tremor filtering and motion smoothing, just filtering methods. No tasks are done yet by the robot. That is introduced at level 2, where small tasks are done by the robot, but mostly the surgeon is taking control of the surgery. At level 3, we give more tasks to the robot, less to the surgeon. The surgeon gets just to watch more and only do the complex tasks. At level 4, we pretty much give all the tasks to the robot, but the surgeon is there ready to take over at any point if necessary. At level 5, there is no fallback option, i.e. there is no surgeon. It's just the robot, set it, forget it. Current solutions include the Mako, which is a bone surgery robot, bone drilling, and highly invasive surgery. Then you have things in minimally invasive surgery, such as the Da Vinci system for soft tissue surgery. And then these systems currently are around level 1, with new studies coming out, new emergence of level 2 autonomy. But there are some outliers, such as the CyberKnife. The CyberKnife is a radiation treatment robot. Essentially, if someone has a tumor, surgeon goes, sets it up, aims it right at where the tumor is, and then it just beams some radiation, killing all the tumor cells. And this is considered a level 4. That's important because right now we are trying to achieve a level 2 autonomy for robotic-assisted surgery. So for the major project, we want 2 robots working in tandem, one using this electrosurgery tool for cutting tasks, and then one using this Da Vinci grasper for grasping tasks and skin manipulation tasks. The Capstone is going to focus mostly on that grasper and designing autonomous controllers for it and a semi-autonomous controller interface for these grasping tasks. So the major project has had 2 works done. One is published, one is under review. The published one, a confidence-based shared control strategy for robotic electrosurgery, is published with IEEE. And the second one, a collaborative path planning strategy for robotic soft tissue surgery, is currently under review at JMRR. Now the overall test bed for these 2 is we have a UR5E robot, whatever tool, in this case it's electrosurgery or electrocautery tool. Then we have our test sample, a light source for uniform lighting, an RGB camera which allows the robot to see what's going on, and then RGB cameras, 2 RGB cameras that allow the surgeon to see what's going on. And the surgeon can see what's going on using a head-mounted display, which is a Quest 3, as you can see here. And the surgeon can control these robots, or this robot, with a haptic device and a 3-stage foot pedal. So there's 3 pedals. This allows the surgeon to switch modes from manual to autonomous and back to manual. And then the haptic device allows them to control, when they're in manual mode, the cutting tasks. And this is what we did for the electrosurgery tool. So for preliminary work 1, a confidence-based shared control strategy for robotic electrosurgery. Like I said, Timo, Meza, and Toha, he designed an autonomous controller for electrosurgery, allowing the robot essentially to follow points that are placed by the surgeon to go through and cut. And then, because we can't just jump to level 5 autonomy, we add mode switching, which brings us to level 2, allowing the surgeon to take over at any point. He also adds a confidence-based mode switching, essentially means that, hey, the robot says, hey, I have a gap here, I'm not confident in this area, I can't exactly see what's going on here. Either A, you need to take over and do the cutting, or B, redo the path so that I can see better, essentially. And we can see that here. So everywhere it is confident in cutting is green. Everywhere it's not confident, there is no line. And you can see here that switch from the surgeon switching into manual mode, going in the unconfident area, and then switching back to autonomous. In preliminary work too, we kind of set the groundwork. This project took a really long time as we found some small problems in the the pilot testing. But Alina C. Kraus, she made a path planning algorithm that essentially the surgeon uses the haptic device to go and place multiple points, and then the algorithm will make a path of least cost using a cost function to avoid the tumors or the obstacles and try and make the lowest cost path without going too far away from these obstacles. We did some testing with this, and we had pilot test, preliminary test, and then true participant testing. After the pilot test, like I said, we noticed some errors, and I'll get to that in the next slide on what we did to fix those. But for the last two tests, we had a training scenario, which was this this card with some dots on it. And then for the actual testing, we had these tongues. So the participants would go through, and with this scenario, they would do two tests. They would start either on the bottom or on the top, and then do a full circle. Or for the second test, they would start either on the left or on the right, and then do a full circle. And they could choose either direction to go. For C, they would start either on the left or the right, do a figure eight. And for D, they would start either on the bottom or the top and do a figure eight. So the problems that we ran into with the pilot test was essentially when you have a haptic device and you're in a 3D area but working on something that's close to 2D, when you start to pull too far away from the surface or push too far into the reference surface, the point gets very jittery and makes it hard to place these points. So we fixed that using a visual cue, which you'll see here. When you pull away from the surface, the dot gets bigger. It looks like it's coming to you. We try to make it intuitive. And then when you push in, you'll see the dot will start to disappear. It'll become more transparent, make it look like it's disappearing out of view. And you can see some of that shakiness there. Another way we fixed this was adding a haptic feedback. So the haptic device would actually pull and push you to try and keep you on the surface of that reference area. And this is mostly what I worked on, was the visual cue, this haptic feedback. I did a little bit of fine-tuning with the algorithm, the path planning algorithm, and I ran the preliminary and final testing for this. And then for the other project, I had worked on the 3D printed tool mount for the electrosurgery tool and the actual test plate where the testing sample would be. And here you can see me using the system as a participant would. In this screen, that's what you would see in both eyes, those pictures. When you see them with both eyes in that Quest 3, they overlap, giving you 3D image. That way you can better accurately determine what's going on in the scene. So the proposed solution for this capstone is we're going to use that UR5E again, and we're going to use this RGB camera and stereo camera. But now we're going to add this DaVinci grasper using an adapter developed by researchers at Southern Denmark University. To test this system and to test the autonomous controllers, we're going to do a push pin picking task. Essentially, we'll have thumbtacks in like a tongue, and then we'll mark it with the path planner, and then the robot will go and grab that point, or grab that thumbtack, remove it, and hopefully not mess up the tongue. And then another test we'll do is a touch test where we'll put markers down, and then we'll test the run out of the system, because the tool itself rotates about its z-axis, and when you have that on such a long piece, you can have a run out, so it moves side to side a little bit when you rotate. The overall architecture for this is we have the testing sample, which is seen by the RGBD camera, which allows us to select points, and then we can feed those points to the trajectory planner, where it plans, tells the robot, hey, this is where you need to go there, and the robot says, hey, I'm here, what's the next step? And it feeds back into the trajectory planner. Risks with this capstone is, first, hardware reliability. If any of these parts break, that's a big no-no, that's not great. But we do luckily have a few extras of a lot of these components. The only thing we don't have an extra of is the DaVinci tool itself. But we're going to be testing everything rigorously using simulations, because I do not want to break a $50,000 robot. Another thing that could be a problem is errors in the kinematic chain. Because we're adding such a large tool, it can kind of throw off the robot. Obviously, you have to tell the robot, hey, you have this massive piece on you now. Here's where your actual tooltip is now, and this is what you just had added to you. Again, we're going to test that in simulators, which I actually already have tested this in simulators, so we know that the kinematic chain is good. And then lastly, control loop latency. If there's too much lag in the system, the robot can obviously crash into something, not respond as fast as it needs to. And again, we can test the codes using the simulator. I've been talking about the simulator a lot, and that is what we have as a prototype for now. We have the tool modeled in a 3D environment, and we're using the old simulator from the electrosurgery tool. And you can see here in manual mode that you do not want me as a surgeon. I have very shaky hands apparently. But you'll see in a second, I'm going to switch to autonomous mode, and it's going to start to do the legacy cutting tasks, because that's just what's programmed for it right now. But as we go on with this capstone, it'll do those grasping tasks where it goes down to the point, and then comes up, and goes to the next area, down, and up. Another prototype we have is the actual hardware itself and the control for the semi-autonomous part. So this allows the surgeon to use these pedals to manipulate and turn, and then the haptic device allows you to do the grasping task, which is more intuitive because there's two buttons in there, one for open, one for close, and that's what you're using to move the robot anyway. So design requirements. Everything in green has been completed, everything in red has been uncompleted. Pretty much the only thing that I haven't fully completed is validation for most things, and then actually making the trajectory planner itself. But like I said, we plan to integrate using the adapting the controllers from Project 1 and Project 2. I'm going to try and do this over December. I have a long break and I have nothing going on, which is awesome. I'm going to try and get ahead and do all that. And then in January, we're hopefully going to test everything in simulations. And then February, get to begin real-world testing. And then finally, in March, we'll try and do final testing. And I try to give myself month breaks. Realistically, these two are going to blend together. It's just how it works. And I wanted to give myself some extra time because I know things are not going to go well. There's always something unforeseen. But yeah, and here are my references for this PowerPoint. Thank you. Any questions?
So you guys are planning on just implementing the system on the tongue, or are there any other like desired testing environments or like objects that you guys are going to be using?
Just for now, we're going to be implementing it on tongues, specifically pork tongues, or porcine tongues. But we have a couple fake tongues that we'll do like the very, very beginning testing on, and then once we get to like participant testing, we'll switch to pork tongue.
Can you operate on a tongue more than once? Or do you guys have a bunch of tongues in the freezer somewhere?
We usually have a bunch of tongues in there. Especially for the electrosurgery one, we take up such a big portion of the tongue, we usually use one tongue, because the tongues are like this long, so we can split it in half and then use it twice, essentially. But, yeah.
So you were saying you were going to pick up and place push pins?
Yes.
What kind of, why would you use that in surgery? Is it just for better control?
This is more so just for accuracy testing, because realistically, it's pinpoint, so in real surgery, you'd be going to manipulate the skin and like pulling the skin back, but we're just gonna show that kind of with the push pins that, hey, you can go to a position that's marked and then manipulate it as needed.
Yeah.
Yes. Dr. Frank.
You had said that there were two robots, one for cutting and one for grabbing.
Yes.
Is your proposal going to be using both, or is it just the grabbing part of it?
Just for this proposal, we're only using one. We're only doing the grabbing part. For the so this is a part of a bigger project that's been going on for years, and a few years now.
Right.
But the end goal is after this is implemented and we get someone to essentially work on bringing those two together, we can have the two robots come together and work on this.
But your proposal is working on just the one robot?
Correct.
Who your ideal participants is? Like, who are you going to test it with?
Well, we really don't have any ideal participants. It's just essentially whoever we can get to come and test it. We don't want, obviously, a very, very specific set of people. We want to keep this diverse to show that our system is robust and diverse and can be used in a surgical setting.
Have you thought about like, maybe talking to the nursing department and see like,
That would
because
be
you do
really
some
cool.
fine tasks, so like just testing it on their students and see like
That'd be really cool.
something.
That'd be awesome. Do that. Get people from the actual medical field to
Yeah.
do it. Any other questions?
Okay, so, okay, go ahead.
Do you have any like real-time data from actual surgical procedures? Because like with like the in the simulated environment with watching the manual versus autonomous, like it's very shaky when you're doing.
Yeah, that's
it,
because
so
we don't have
I-
any tremor filtering
Yeah.
on that portion.
Yeah.
I do want to add that for that portion. We don't really have, I don't think we have real world other than from what we've done with participant testing,
Mhm.
but
Okay.